A2 further maths, differential equations, integrating factor. Okay, so what I'd like you to do first of all is just have a go at, by using your skills from normal maths, I would like you to have a go at finding the general solution to that differential equation right there. So you want to pause it and have a go yourselves, please. Okay, so hopefully what you thought about doing is exactly what it says on top, separating out the variables. This is the only way you know of solving differential equations, and it's the only skills you need to know for normal A-level maths to solve differential equations. So when we talk about separating out the variables, we're talking about putting all the x variables on one side and all the y variables on the other side. So we do it something like this in this case. Notice we put all the y variables on this side and all the x variables on this side. And we keep the dy over dx. I know it's very easy to think we can separate out this dy and this dx as if it's just a normal fraction, but mathematically that's not quite correct. So it's better to leave it as dy over dx just here. Once we've got it as dy dx, we can now integrate both sides in terms of dx. That's why it's important to not just separate these two out, because you're integrating both sides in terms of x. So we get this. The two dx's there will cancel out, leaving you the dy, which means that you can then integrate this side in terms of y and integrate this side in terms of x. So it's exactly the same as what you do in your normal maths, but just that extra bit of understanding there about y when you integrate both sides is within the same term that you integrated. So what do we get? We get 1 over y dy there, 6x squared dx, and then from there we can integrate that. And don't forget to put the plus c. It's absolutely vital, because without that plus c you have not got a general solution. You will have a particular solution. So in this case we've got our general solution sorted. We can put the c value, we can take the one over the other side and do the exponential of both sides. We can put that up as a power, and then of course that plus c there can be written as e to the c, which is another constant. And because it's just another constant, we can move it to the front. So we end up with the general solution of ae to the 2x cubed. So we've ended up with that solution just there. Okay. Right, so what I'd like you to do is, using those skills, have a go at solving this one using the same sort of skills that you got from your normal maths. So just pause there, have a quick go yourselves. Okay, so hopefully you realised relatively quickly that it didn't matter how hard you tried, there was no way to separate out the variables in this case. Right? It doesn't matter what you tried to do, there was no way of just getting all the y's on the one side and all the x's on the other. It just wasn't possible. And that's because not all equations, not all differential equations can be solved by separating variables. It's not always possible. This is a good example of one that's not possible to solve by separating the variables. So if they can separate, in which case all the ones from your normal A-level maths are separable differential equations. So if they can be separated, and you can put all the functions in terms of y on one side and all the functions in terms of x on the other side, then you've got what we call a separable differential equation. And you can solve it by doing that sort of skill. Put all the y's on one side, put all the x's on the other, integrate in terms of x for both of them, and then solve to get a differential equation, or solve the differential equation to get a general solution. But the problem is, not all can be separated. And so how do we go about finding a solution to a differential equation like this? How can we find a solution to this if we don't separate the variables? Okay, so what I'd like you to do, just first of all, is just have a quick look at that side. Okay, so that side of the equation, the x squared dy over dx plus 2xy. And what I'd like you to do is just have a think, what can you notice about that? Okay, so pause there, have a good think about it. What do you notice about that side? Forget the equals 5 for a minute. Okay, so well done if you noticed that that side of the equation can be written like this. Okay, so if you think about it, and what you might have noticed is that really we have x squared there, and this is you differentiating y. So we've got x squared differentiate the y, plus leave the y alone, and differentiate x squared to get 2x. Okay, so I notice that x squared there differentiates to get 2x. That bit there differentiates to get that. So I've noticed that this consists of the x squared, which differentiates to 2x. So that bit differentiates to there. And I've noticed also that this y differentiates to dy of dx. So those two parts just there are almost, if you'd done differentiation on a function, if you differentiated a function, x squared y, because if you differentiate x squared y, it would go to that. So it's noticing that you've actually differentiated the function x squared y. So what we can do is we can rewrite this. Yes, we use the product rule to differentiate x squared y. So we can say that if we differentiate the function x squared y, we would end up with this function just here. Okay, and you've seen that recently with your implicit differentiation. When you implicitly differentiate x squared y, that is what we got. Okay, now this is just in reverse. It's noticing it and saying, oh yeah, look, I can see this, so therefore I know it's this. Now it's not obvious, and there's going to be techniques we're going to look at in a little while to do it a bit more organised, a bit more mathematical than just being able to spot it. But it's the reason why this seems to work later on. This idea of separating out using the product rule. Okay, so we got that point just there. We know we can write this part as the differentiation of x squared y. Now, because I can write this as the differentiation of x squared y, all I need to do now is just integrate both sides in terms of x. If I integrate both sides in terms of x, if I differentiate it and then integrate it, I should end up with just that bit in there. Okay, so that's what I'm going to do. I'm going to integrate both sides in terms of x. Done that. Done that. This is really easy. Okay, because it's differentiate x squared y and then integrate that result means they cancel out, like I just said. So I've got x squared y just there. The integration of 5 in terms of x is going to go to 5x plus c, because I want a general solution. What's the answer at the end then? Well, if I want a y equals answer, I could write 5x plus c all over x squared. And what you could do now is you could just try to substitute that back in. So have a go, differentiate it. So you can substitute it in there. Think of when you differentiate this, you could think of it as 5x over x squared. So that's 5 over x plus c over x squared. Okay, keep the c in there, c over x squared. I do want you to have a go, so I want you to pause, have a go at substituting that in for y and differentiating it, substituting there, and just check that when you add those together, do you get 5? Okay, so pause there before you move on. Okay, so hopefully you would have found that that solution does work in this differential equation. Everything seems to cancel out, leaving you just the answer of 5. Okay, so let's have a look at another one. So now we've got that idea that we should be able to separate this by using the product rule by thinking what differentiates to make that. Now the problem is in this case is that when you look at this function just here and you think, right, I've got 2x there. If I differentiate 2x, then it's going to go to the number 2, so I need a 2 here. Realistically, I need a 2x because it's to differentiate the y, leave the x part alone, so I can get a 2x here. But if I do something simple like just multiplying both sides by 2, just both parts by 2, what happens is when you times it by 2, this part changes as well. So now you think, oh, actually I need a 4. Oh no, I've only got 2. So it's not as simple as just saying I'm going to multiply by something to get these two the same. Okay, it'll also affect this side of the equation as well. So be very careful about thinking about multiplying. I'm not saying you can't do it, but it wouldn't actually help in this case, right? Because both things get affected, both terms there get affected. Okay, so what can we do then? Is there some sort of function that we can multiply by? 2 didn't work. Is there some sort of function we can multiply by that actually means that this can be solved using the product rule? Okay, and the answer is yes. You can't do it by multiplying by 2, but you can do it by multiplying by an exponential function. Now this wouldn't seem that logical. I wouldn't expect you just to know this at all, but we can multiply it by an exponential function. There's a couple of reasons why you'd use an exponential function. First thing, the exponential function is really quite nice for differentiation because it doesn't change. So if I do e to the x squared, for example, when I differentiate that, I know part of it will be e to the x squared. So the same multiplier will be in there and there. Okay. Also, the power of that x squared, e to the whatever it is, this is in case it's x squared, can be manipulated to be the answer to this. So e to the x squared, well, x squared, the reason why I pick x squared is because it differentiates to 2x. That's what it's saying there. Notice that the x squared I picked as a power. I just seem to randomly pick e to the x squared, but it wasn't random. It was the fact that x squared differentiates to 2x. Okay, and that's where I've got this thing from. Okay, I've multiplied everything on both sides by e to the x squared. Okay, now the reason why I do that then is because now if you look at these two functions just here, they actually seem to work. Leave alone, differentiate the y, differentiate e to the x squared, leave the y alone. So there's leave it alone, differentiate the y, differentiate e to the x squared using the chain rule, leave the y alone. This side we can just neaten up. We can just leave that alone and just play with that later. It's this side you should be noticing that now that I've multiplied by e to the x squared, I haven't changed it because it's the same constant throughout. Sorry, the same function throughout. So therefore I haven't changed it, but now I can use this idea of rewriting this using the product rule. So this would have been the product rule of me differentiating e to the x squared, because that's the bit you left alone there, y, because that's the bit you left alone here. So e to the x squared y would have been my function that I would have differentiated. Okay, so that differentiates using that rule. Okay, so d, and don't forget that's nothing to do with this, that's all to do with this part, just noticing that that's the same as differentiating e to the x squared y. Right, so that means what I could do is I could rewrite this side just here as this. This side I can neaten up. Remember that when you times, it's like adding the powers. So e to the x minus x squared plus x squared, the two x squared parts will cancel out. So the x squared and the minus x squared, leaving you just e to the x. Okay, so this differentiates to that. This is what the result of that part. Right, what do I do now? Well, now I can integrate both sides in terms of x, which means I've got a simple integration to do on this side. This side cancels out with that d over dx, not dy over dx, the d over dx. A d on its own means you're differentiating this function here in terms of x. Okay, it's very different to that. Okay, that's saying differentiate just y, whatever y is on its own. Okay, so be careful with your notation. But because this is basically saying differentiate and then I integrate before it, they do cancel each other out. So that's why you end up just this part. What's this? This is integration of just that side in terms of x, which of course is just e to the x plus c. So there's my integrating that part. What does that mean then? Well, I've got y equals e to the x plus c over e to the x squared. And just as it was before, just pause there, just check and confirm that you're happy with that. Don't just go, yes, I'm happy with it. Actually have a go at writing this. This one's a bit more complicated. You want to probably think about you writing this as e to the minus x squared and expanding the brackets. Okay, so times that by that and then that times that, and then have a go at differentiating it then. Okay, but do it, differentiate it, substitute it back in the original, just confirm you get that correct result. It's a general solution because we don't know what the c value is, of course. Right, so hopefully you had a go at that. Grab your notebooks then, please. Let's just try to put this a bit more formally in our notebooks, but also trying to work these things out without having to do all the manipulation and things like that yourself. Okay, so if a differential equation can be written in this form, so all the differential equations we've just been playing with have had something in common. And what they had in common, those two differential equations we just looked at, was they can be written in this format of dy over dx plus some function of x, y. And that is the important bit. It has to be a y and it has to be dy over dx there. This side has to be in just terms of x. The moment this has got some function of y on here, or maybe this is something different to just single y, maybe it's something like y squared, then you cannot use this technique. We need to look at other techniques. So you're looking for this dy over dx on its own, function of x, single y, not a function of y, a single y value, and then a function of x on this side. And so that's the sort of thing you're looking for. Now in the exam, it's highly likely that the examiner will tell you using an integrating factor, and you expect to rearrange this sort of format. There's other techniques you can still use instead of this one, so it will be majorly hinted that you have to use an integrating factor. So in your notes, please, just get that down. So that equation can be solved by multiplying by what we call an integrating factor. Now, an integrating factor that you can work out looks like this. So the integrating factor is always an exponential. The exponential is used to find it. And you integrate the function in front of the y as the power. So you need to take that function, whatever it was. Remember last time it was e to the x squared. So we take that function, we integrate it, and that becomes the power of the exponential just there. So whatever function that is just there, we integrate it and that becomes the power. So e to the whatever the integral of that bit is. No need to rearrange, no need to try to spot it yourself. You can just use that rule and you will always have your integrating factor. Okay, once you know your integrating factor, then you can multiply everything by that integrating factor. So whatever it is. Okay, and you'll see some examples where the e and this part here cancel out to leave you something nice. All right, they're not always e's, because if you've got an e and then a none up here, they will cancel out, leaving you an integrating factor that doesn't involve exponentials. So just be aware, it doesn't have to involve exponentials at the end. So I've got e to the whatever, that's my integrating factor. I've times everything by that integrating factor. And then once you've done that, what happens is you can now put it together. Because the reason why that's worked is if you look at, let's say, this function just here, because you've got the chain rule, because you're using chain rule just here, this is your integrating factor, whatever this is. If I differentiate that, okay, if I differentiated this, what would happen is I'd use the chain rule and I'd say, right, I differentiate the inside function. Now, if I differentiated the inside function, the differentiation of the integral will cancel out, leaving you just px, okay, times by e to the whatever. Now, that's just going to be exactly the same as this. That's the beauty of the exponential function. So we can just call that I as well. So there's I, there's the differentiation of I. But because the exponential function, I is within it as well, okay? So it's the outside function, inside function. Right, so now I've got that, I'll also notice that y is the function left alone there, and it's differentiated there. So left alone, differentiated, differentiated, left alone. That is your product rule right there. So because this is a product rule, what I can do is I can look at integrating both sides now. And I've noticed, also don't forget to multiply by I on this side. It's a very easy mistake for not to forget it. So I've integrated both parts. I've noticed that this bit is just going to be my product rule. So I could write this as the two left alone bits. So it's leave alone, differentiate, differentiate. So it's these two parts just here that would have differentiated. So differentiate IY. So when I integrate and then differentiate it, I end up with just IY. Now that is your general solution to this differential equation. So that's the beauty of it. If you can see it in this format, if you can put it in this format, if you can work out your integrating factor, then you can jump straight to this answer down here and just write your integrating function with a y after it. So whatever it is, put a y after it, equals the integration of this side times by I. And this side might be really easy to do. Okay, so you could jump straight to this bit. Okay, so pause if you need more time. Okay, so let's have a look at solving one of these equations using the integrating factor technique. So I want to solve this equation using the integrating factor, given that x equals 2 when y equals 1. So therefore I can find a particular solution, a natural solution to this differential equation. Okay, so the first thing I want to do is just confirm that it can be written in this format. Sorry people, if you need more time or you want time on it to have a go on its own, just pause it there. I haven't done anything too big there. Just pause it, have a go through yourself. Okay, apologise for not saying that earlier. Okay, so you might have had a go yourself now, or you might want to just follow it through slightly. So the equation can be written in that format. Right, the problem is, as you can see, we haven't got it in that format. I've got an x there. There shouldn't be an x. This needs to be on its own. So I need to just maybe do a bit of rearranging. I can do that by dividing through by x. The other thing I want to check is, does this just have a function of x in front of a single y? Well, it says 2y, but that's okay. Right? Y squared would be a nightmare. I wouldn't be able to do it with y squared, but I could do it with 2 because I could just put that as part of the function x. So 2 over x, for example. All right, so that's fine. 2 over x can be my px. This side, have I only got x's in there? There's no y's. Yeah, that's fine then. Okay, so I can definitely see by just dividing through by x. Just dividing through by x shows that I could write in this form. dy over dx on its own, some function of x, y equals some function of x. So big ticks, we're allowed to use an integrating factor. So the integrating factor, you need to learn it off by heart, is e to the power of the integral of this. So in this case, I can use this formula as long as I know the integrating factor. So I can use that formula if I know what the integrating factor is. Okay, so how does that help me? Well, I can now work out this integrating factor. And that's where, again, you might want to just pause and do it yourself. So you can work out the integrating factor, and I'm going to get this. So the integrating factor in this case is e to the integral of 2 over x. Now, 2 over x, like I said, 2 out if I want to, it's the integration of 1 over x, which of course is just ln x. So the 2's come to the front because I took it out, so 2 ln x. To me, I could take the 2 off and make it x squared, and then the e and the ln will cancel each other out, leaving you x squared. So in this example just here, the multiplying factor of x squared would mean that these two things will work. Okay, so x squared will be my integrating. By work, I mean be able to use the product rule. So let's just do the next part, which is multiply through by the integrating factor and then write this possible result just here. So the result I'm going to get could just be, without having to do all the work on this side, x squared y equals the integral of x squared times that. So x squared y equals the integral of 3x squared, this. Okay, be careful. Notice it's not multiplying x squared by this, it's multiplying x squared by this. Okay, so be very careful. Don't make the mistake I almost circled there with my pointer, remembering that this was your rearrangement, so this is what you multiply by x squared. That was your function q of x. Okay, so I'm multiplying by x squared, so that bit there just goes to iy, and this bit goes to 3x squared root x cubed plus 1 dx. Now I'm going to have to play with this a bit. I'm going to have to do an integral, but that's fine because I haven't got a situation like this one where I've got lots of x's and y's floating around with some dy over dx's. I'm pretty much home free now. Okay, I just need to sort out this part. Okay, so let's have a quick go at sorting this out then. To me, I've noticed that I've got an x cubed there, and that's an x squared there. In fact, I've got an x cubed, and that's a 3x squared. So I can see that it's going to be do some differentiation of this. So that's what I'm going to do. Integration by substitution. I'm going to let u equal my x cubed plus 1, and I can differentiate it, and I get my du equals 3x squared dx. Okay, which means that when I substitute that in, that 3x squared and that 3x will cancel out. And that's going to leave me du as the subject, as the what I'm integrating in terms of. And of course, this bit could be written as u square rooted, which is u to the half. All right, so just convince yourself you're happy with that bit using that. Okay, so now I can definitely integrate that because I can add 1 to the power and divide by that new power. There we go. plus c. Don't forget the plus c. It's very easy to miss that out with all this other complicated maths going on. But you need that plus c because we need the general solution. Once I've done that, what I'm going to do is neaten it up, times it all by 3. There we go. So, and just notice that I've changed my letter. And if you're thinking, why has it gone from a C to a K? What I've done is because I've times everything by 3, that would go to 3C. Now you could write 3C there, but there's no point in writing 3C because 3C is still a constant. I'm just going to change it for a different letter. You could have it C1 and C2 if you really wanted. Okay, so you've got a different constant just there. We call it K. Okay, so now I can actually finish off and find the definite answer to this differential equation. I can find the particular solution because I know that when x equals 2, stick 2 in there. All right, when x equals 2, y is going to equal 1. So I can substitute my value in. I could do the number crunching. So I've substituted in the 2 squared, I've substituted the 1, and so on here. Then if I do that, I get the number. I'll do the maths for you. Gets you k equaling minus 42. Okay, so just pause there, take notes. So we've got the solution of 3x squared y equals 2 lots of the square root of x cubed plus 1 all cubed minus 42. So a nice straightforward answer there to finish it off, but that is your particular solution. You don't have to rearrange it and make y the subject unless it asks for you to make it explicitly to do with y. You can just leave it like that. In this case, we have completed our differential equation there. Okay, so before we have a go at a few more of those, I just want to look at some slight differences, and they'll always give you these hints in your questions on how you can actually transform it. But I want to see if you can spot how you could write that differential equation just there, what's called a second order differential equation. What could you use as a substitution to show that that is definitely the same as this, or definitely written as this? Okay, so I'm going to stop and let you have a think about it. Okay, I wouldn't expect you to necessarily spot this because it's not straightforward and it's not as easy as just saying I'm going to just divide by x and therefore it's the same. If I just make this one the gradient function, this one the x, it doesn't quite work like that. The way you're going to have to do it in this case is by using a different sort of substitution. And the substitution I'd expect you to use is one that would be given to you in that exam, all right, or be given to you in the question. They wouldn't just expect you to just do something like that yourself. So the first thing I'd like you to do is just try that. Okay, so grab your notebooks, write it down, but then just try it yourself to show that I could write that in that form. Okay, so let's see if you manage to do it then. So I would say that if I let u equal that, then that's definitely going to be u. All right, so I'm going to get 1 over x u. So u will become the y, the y variable. This part here, though, it's not just as easy as going u squared, all right, or replacing it and writing it as du dy over dx all squared, or anything silly like that. What I need to do is just have an understanding of what this actually means. Now, this means a second derivative. This means you're differentiating the first derivative. So why you could write it, think about it, would be like this. The second derivative is you differentiating the first derivative. So you differentiate the first derivative in terms of x gets you d squared y over dx squared. That is why, if you look at it, you write it with a square next to the d there and the square next to the dx at the bottom. Okay, because you're doing that times that is d squared, that times that is dx all squared. That's the reason why you put the two squares in those places. Okay, now why does that help in this case? Well, I know what that is. That's the u. That's my substitution. So really, this is going to be written as du over dx. Okay, that can be written like that. So therefore, I could write this as d over dx u, which is where the du over dx comes from. This can be written as u, and therefore, can I write it in this sort of format? Yes, once I divide through by x. And then you could go on and you could solve it, you could find the integrating factor and so on. And that's what we're going to look at. So just pause there if you need more time for your notebook. Okay, so by transforming that into that, which is what we just looked at, can we now find the general solution? I want to pause. I want to give you a chance to work out the general solution yourself by finding the integrating factor and then rearranging and sorting it. Okay, so have a go at that yourself. And in this case, you do have to make you the subject at the end. So let's see how far you got then. So did you notice that it was minus? That was important. So minus 1 over x was your integrating factor. Remember, it's always p of x, which is plus minus 1 over x. What does minus 1 over x go to? Well, it goes to minus ln x. How does that help me? Well, the minus can come up to the power, so that's x to the minus 1, and the e and the ln will cancel out, leaving you x to the minus 1 or 1 over x. So well done if you managed to get that as your integrating factor. Once we've got our integrating factor, we know that on this side of the equation, this part just here is just going to go to 1 over x, y. That's the integrating factor times y, which means it's just going to go to y over x. This side here was x squared ln x, here it is, but I divided by x, so it's x ln x. So this part I need to work out to integrate. So there's the first bit. I know this part now is going to go to 1 over x times by, I said y because I was talking about this one, but of course in this case it's u. Now I've done the substitution. So I've got u over x. This side I've multiplied by I, so it's 1 over x, x. So these two are going to cancel out. Okay, so the integrating factor times this is going to cancel out, leaving me rather irritatingly just the integration of ln x. If it was x, it would have been a bit nicer. But what can I do with that then? Well, I can still integrate it. And you guys know how to integrate it already, but it's worth seeing again. How do I integrate ln x? I'm going to use integration by parts. And I need to be careful when I use my integration by parts, because if I use that as my u bit to be differentiated, it'll be fine. But if I use it as my bit to be integrated, I'm back to where I started. And there doesn't seem to be two parts, but you can cheat. You can write it as 1 ln x. It's the same thing. And why that helps me is the 1 can be the thing you integrate, and the ln x can be the thing you differentiate. So my u equals ln x, and my bit I'm going to integrate, my dv over dx, I'm going to write as 1. What do I end up with is this goes to 1 over x, and this goes to x. Okay, so it seems to be getting more complicated. But now when I put these into the formula, I know I get x ln x minus the integral of these two put together, which gets me 1. And then so I'm integrating 1 in terms of x, which gets you minus x. You should know that off by heart. You should definitely know how to show it. Okay, so all of you need to know that for your normal maths, never mind your further maths. So what do I end up with then? Well, the integration of ln x is x ln x minus x. There we go. Plus my constant of integration. So can I get u on its own? Yes, I can, if I times through by x. Notice what's important here is our constant, our c value, becomes cx. I can't convert that to another constant because x is a variable. I have to leave it as cx. Unlike last example, where I just times it by 2, and 2 was a constant, I could change it. This one I can't. Right, so there we go. I've got that. That's my integrating. That's my integrating factor used, and that's my general solution. But there is an issue. U was dy over dx. So really, if I want to work out what the y value is, the general solution to this equation just here, I'm going to have to do something with this. So just pause if you need more time. Okay, so I'm going to take that. I'm going to replace that u back to dy over dx. And now I say, right, can I actually work out the answer to this? And yes, you can, because it's not that bad, because really they're saying this is the differentiation. What I can do is I can just integrate both sides in terms of x. This will get me what y equals, or just y equals, and this bit I can just integrate using my integration skills. X squared ln x, can I integrate that? Yes, you can. All right, when you integrate ln x squared ln x, it's not as bad as it looks. You're doing by parts again. That's the bit you can integrate now that we've shown it, but it's better to use that as your differentiation. and that is your dv over dx. And so it's not as bad as it looks, because this goes to 1 over x, this goes to a third x cubed. Okay, so it's got more messy. That's why you usually differentiate the polynomial functions, because you integrate them to get more messy. But these two will end up getting times together, which means there won't be any lunds next time round. So that's going to be those two bits put together, and that is your minus the integral of these two, which is x squared. That's why it goes back to x cubed. So well done if you got that. Okay. Obviously, the minus x squared is going to go to x cubed over 3, and the cx is going to go to cx squared over 2, plus another constant, which I'll call d or k or whatever you like. Just don't use c again. Okay, so you should have an answer like that. Very well done if you managed to follow through all that. What I'd like you to do now is go away and have a go at practicing some of these differential equations using the integrating factors. Just pause there if you need some more time for your notes. I've just simplified it there at the very end, just putting the two x cubes together. And there you go. Have a go at those exercises on page 256.